think we're in business. So, any questions? Okay. So I want to talk about inverses today. So we need to review that before we dive into trigonometry. So if you recall from your college algebra course, for example, if you have a function that's defined like this, so nice little function, just three little ordered pairs, nothing else. If I ask you, for example, what is f of 3, you will say 5. And if I ask you what is f of 4, you will say undefined, right? We don't know, right? 4 is not in the domain. Okay? But if we want to talk about the inverse function of f, the inverse function will tell me where the outputs come from. If I ask you what is the inverse of 5, you will say 3. So the inverse functions, they reverse the order of mapping, right? So the function takes us from 1 to 2, well, the inverse function will take us from 2 back to 1, okay? The inverse function will take us from 5 to 3, and the inverse function will take us from 7 to -2. And the special notation for the inverse function is like that. It's not an exponent, it's just a little -1 to represent inverses. Do you remember that? But it might have, oh, is it? Oh, that's, well, you'll have to do some extra reading then. Now, if I plot these points, if I plot the points 1, 2, 3, 5, -2, well, I guess 7 over here, and at the same time, if I plot points 2, 1, 5, 3, right, and then 7, -2, so the pattern is these points are reflected, well, over the line y equals x, right? That was the not drawn to scale thing, but if I fold it over the line y equals x, these points overlap. And this was the general idea what we had when you're sketching a graph of a function and its inverse, you reflect it over the line y equals x. That's how you can produce a graph of the inverse. Does that ring a bell? For example, if I give you this function, let's say it has a point 0, 2, maybe 2, 1, and 4, 0, something like that. There's some function f. And if I ask you to sketch the graph of the inverse of that function, you will say, well, the original function has a point 0, 2, so the inverse will have a point 2, 0, right? The original function has a point 2, 1, so the inverse will have a point 1, 2, right? And the original function has a point 4, 0, so the inverse will have a point 0, 4, right? And then I'll just try to connect those dots with this type of reflection. So what is it going to look like? Something like that. if I fold over the line y equals x, these two graphs overlap. Will they overlap? Okay, close enough. Okay? Happy? So, do all functions have inverses? What can stop us from getting an inverse of a function? Does anybody remember? Not one-to-one. What on earth does that mean? Okay. Passes the horizontal line test, because here's an example. So good, you guys remember some things. Is this a function? Well, I called it a function. I wrote f of x, so you can just say, well, that's what you said, but it is a function, right? But if I try to reverse all the ordered pairs, I'll get 2, 1, 2, -1, 5, 3, 7, 4, right? Now, is that a function? No. This is some relation, but it's not a function. Why is it not a function? Right, so there's 2 points. You have the same input, 2 different outputs. So that's not a function. If I were to plot these points in R, you'll have 2 points directly above each other, so it fails the vertical line test. But here, if I plot these points, you're going to have these 2 points that are on the same horizontal. So it will fail the horizontal line test. So we do have this definition of a one-to-one function, that for every x you have a unique y output. And actually for every y in the domain, in the range, you have a unique x in the domain. That's a better definition. So let's write this down. So one-to-one functions, actually let's do it here. So definition of a one-to-one function. So a function has to be one-to-one in order to have an inverse. So for every y in the range, that's the range, there is exactly one x in the domain. So again, think horizontal line test. Is that okay? Let's go back to my very first example. Here's the function f. What is the domain of this function? I'm going to label it d with a little f. Domain of f. What is the domain of this function that I wrote originally? -2, 1, 3, just 3 little points, right? That's the domain. Well, what is the range of this function? 2, 5, 7, just the y values, nothing else, right? But if I look at the inverse of f, what is the domain of the inverse? 2, 5, 7, you just look at the x values. 2, 5, 7. And what is the range of the inverse? Yeah, it switches. So we made a big deal out of that in college algebra, that domain of the function becomes the range of the inverse, right? And the range of the inverse becomes, well, and the range of the function becomes domain of the inverse, right? Because remember, I can draw a function, I can give you a function and say, find the domain of that function, and you should be able to do that with the relative ease. Finding the domain is not hard. Finding the range is hard, because the range you have to predict all possible y values. So if I give you a graph of a function, then you can just look at the y values and say, well, this is the range, blah, 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 okay? But without the graph, the range question is tricky. But if I give you a function and I ask you find the range of that function, you can actually go ahead and find the inverse of the function, and then find the domain of the inverse, because domain is easy. That will give you the range of the original function. How is that piece of logic? Brilliant, that's exactly right. Because again, domain, you just look division for 0, square roots. The range is hard. You have to consider all the y values. But if you flip them and you find the domain of the inverse, you get yourself the range of the original function. Well, anyways, that's a little side note. So now let's write the official definition of a function in the inverse and some wonderful properties that come with it. So let f be a one-to-one function with domain A and range B, then this guy is the inverse of f with domain B and range A if and only if the following works. The two things that need to work in order for a function to be an inverse do you guys recall those two things? Given two functions, what needs to happen in order for them to be inverses? Well, that's how you find the inverse. But if I take a composition of a function and its inverse, what has to come out? X. That's right. So the composition of function and its inverse is x. Because again, if you think about this, the function takes you from x somewhere else, but the inverse takes you from that somewhere else back where you started. So the composition, and it has to work both ways. So the composition both ways has to produce x, has to produce your original point where you started. Because again, if you think about this, if this blob is the set A and this blob is the set B, so if I take a point, let's call it x, from the domain, well then f of x will map it to some point in the range, right? F of x, right? Well then the inverse starts here, right? The domain of the inverse is the B set. Well, so the inverse has to take this point back where you started, right? So this is why the composition of these two functions always produce the original input. Okay? Does that make sense? So let's do an example. I'm going to give you a function . 2x plus 1. Very nice, friendly function. So what is this function up to? What is the function of this function? What does it do? What? It's a line, but be more specific. What exactly is this function going to do to whatever you feed that function? You toss in a 5 into that function. What's going to happen to that 5? It'll get multiplied by 2, and then 1 will get added to it, right? So if you pay attention to the order of operation, first times by 2, then add 1, right? Times by 2, add 1. The inverse will do exact opposite in the opposite order. So if this function first multiplies by 2 and then adds 1, so the inverse is going to subtract 1 first and divide by 2. So it does the opposite operation in reverse order. So here's my guess, and sometimes we can guess the inverse function. So it will go x minus 1 over 2. It will first subtract 1 and then divide by 2. This is just a guess. So to prove that my guess is correct, I will actually have to compute the composition of these two functions both ways. And if both ways produce just x, then yes, these two functions are inverse of each other. So let's just review how we do compositions. Remember the composition notation? The outside function, the inside function. So the inside function replaces the variable. So it becomes 2 times x minus 1 over 2 plus 1, like that. Right? So if I start simplifying that, 2's cancel. So we're down to x minus 1 plus 1, so x. Good. That happened in the past. Is that okay? If I do the composition the other way, it becomes 2x plus 1 minus 1 over 2. So I'm replacing the x in the inverse function with the function. So if you follow the order of operations, 1's cancel, you're down to 2x over 2. So yes. So the functions are inverses of each other. Is that all right? Happy? Now, of course, this process of just guessing is not bulletproof. We need to have some kind of a algorithm of finding the inverses of functions. So I'm about to give you that because, I can make it more complicated. It's going to be hard to guess. So here are the steps for finding the inverses. So step 1. Write y equals f of x. So actually, you need a y in there, basically. Step 2, interchange x and y. And this is the silly step again. For every x, you put y. For every y, you put x. The third step is the really, the important one. That's when you solve for y in terms of x. So whatever you end up with is the inverse function. Let y equal the inverse function. So here's an example. Find the inverse of f of x equals 4x cubed plus 2 over 7. So I want to find inverse. So the first step tells me to do this, right? Y equals the function, so here it is. So this is step 1, done. Y equals whatever the function is. Step 2 tells me to flip x's and y. So for every y I put x, for every x I put y. And now solve. So how do we solve for y? What's the first thing you want to do? Multiply by 7. So it's 7x equals 4y cubed plus 2. Then what? Subtract the 2. So it is 7x minus 2 equals 4y cubed. Now what? Divide by 4. So y cubed equals 7x minus 2 over 4. And finally, yeah, y equals the cube root of 7x minus 2 over 4. So we're done. This is the inverse. This is the first step. The inverse is this. How's that? Is that okay? Now, so let's have a philosophical discussion. In college algebra, whenever you were introduced to the notion of an inverse, it almost looks silly, kind of like, well, I mean, all I'm really doing is solving for y in terms of x. This is like solving equations anyways. So what's the big deal? And why do we even bother with the inverses? And again, the inverses should help us to solve equations, because that's, again, that was the goal in algebra, to solve equations. And let me just show you an example. Solve this equation. So what was the inverse we just found? It's the cube root of 7x minus 2 over 4 equals, oh, really don't care, 3/4. Okay? I want to solve this equation. So how would you go about solving this, by the way? If I just, stop talking and you'll just solve this, what are you going to do? Yeah, you'll cube both sides to get rid of the cube root, right? Then you'll probably multiply by 4 to get rid of the 4. Then you're probably going to add 2 to get rid of the 2, and then you're going to divide by 7, right? Because what are you trying to get? You're trying to get x on one side, right? That's the idea behind solving equations, right? When you solve equations, this is really awful. When you solve equations, you're trying to accomplish this. You're going to take one side of the equation and unravel it so it just has x on one end, okay? Well, let me show you another way to solve this equation. It's a bit of an overkill for this particular problem, but I know how to turn the left-hand side into x in one move. Just one move. I can turn left side into x. Because over here somewhere here, well, it said that if I take a composition of two functions that happen to be inverse of each other, that composition always comes out to be x, right? So having said that, do I know the inverse of this function? Yeah, the inverse of this function is the 4x cubed plus 2 over 7. This is the inverse, right? So if I actually take the composition, let f of x be 4x cubed plus 2 over 7, was that the function? And if I take the composition of both sides, if I actually go f of cube root of 7x minus 2 over 4 equals f of 3/4, then the left-hand side without doing any work is x. Because I know what I just did, I took a compositional function in this inverse, it better produce x. While on the right side, I get a number, right? F of 3/4 is some number, so this is 4 times 3/4 cubed plus 2 over 7, whatever that is, it's some number, so I just solved that equation, right? Again, looks silly to solve this equation by these techniques, but not every function can be solved algebraically, right? Not everything that we do can be just go, okay, add 2, subtract 7, whatever. And first time when you used inverses in college algebra is when you solved logarithmic equations and exponential equations. Remember that? You had exponential functions and you had logarithmic functions, they're inverse of each other. So you used ones to solve the others and so forth. There's the only way you can solve those. You'll see the same thing here because we're going to develop a certain family of functions, trigonometric functions, that we won't be able to solve algebraic. We won't be able to solve equations that involve trigonometric functions by doing our simple algebra steps. So we'll need to, we'll need this. We'll need inverses. Are you with me on that? Felt like I lost you there for a minute. Did I lose you there for a minute? No? Okay. Well, good. So, let's play this game. I'm going to give you, what? Well, it's a boring game, but I'll give you a function. What is this function up to? Squaring things. And if I ask you, can you think of the inverse of that function? What would feel good? Square rooting things, right? Do you agree with that? If one function is squaring, then the inverse function should probably be square rooting things, right? Now, we've done that very example in college algebra last semester, but this is a very classical example to start messing with you. Now, so if this is true, then what needs to hold? How can I make sure that these two functions are in fact inverse of each other? Right. So I want to do compositions, and if the composition works both ways, then we're good. So let's try that. So if I take the composition this way, f of g of x, so I'll just have to square the square root of x. What is that? X. So that makes us happy. But if I go the other way, so this is the square root of x squared. What is that equal to? Well, or the absolute value of x, right? This is what we agreed on last week, and you that showed up on your homework. Not necessarily x, right? So it does not equal to x, so it did not work, right? Now, there's a way to, there's, a little thing we could have noticed that would just tell us that it wouldn't work, and that would be the fact that x squared is not one-to-one function. Right? If you think about x squared, it's a parabola, it fails the horizontal line test, so it shouldn't have an inverse. So that didn't work, right? They are not inverses of each other. Do you agree with that? Just based on this little performance here? That should make us very, very sad. Because if you think about this, we have no problem solving quadratic equations, right? And the quadratic equations and the parabolas, they're so nice and pretty that, we should be able to figure out a way to build inverses out of that. But right now, that didn't work. Are you with me so far? Okay. Well, let's try this example. I'm going to give you this function, square root of x. So this function is up to square rooting things. What do you think the inverse of that function is? Squaring things, right? Okay. Now, is square root of x a one-to-one function? Yes, because we know the graph of the square root of x. And, is that thing that passes the horizontal line test. But if I do the test, if I try this again, I'll do the easy one first. If I do the composition g of f of x, so this is the square root of x squared, that's x, no problem, right? But what about the other way? So what is that equal to again? Absolute value of x. But in this specific example, I can just say, well, in this very case, I can say that. And that's because if I look at this function, what is the domain of f? Right, it's strictly non-negative, right? Just the way it's written, the domain of the square root is just non-negative, so the absolute value in this case becomes redundant. I don't need the absolute value because x is non-negative to begin with, so I can just say x, right? Now, what is the range of the square root function? Again, think of the graph, 0 to infinity. Right? So therefore, from everything that we just talked about, when I look at the x squared as the inverse of the square root function, what is the domain of x squared right now? In context of this scenario, the inverses. 0 to infinity. Remember how the range becomes the domain. And domain becomes the range. Remember that? When we talk about the inverses, the range becomes domain, domain becomes range. If I grab these two functions, see what happens. Here's the square root of x, right? Well, here's the x squared if I only limit it to positive numbers. I don't need the second part of the parabola. And it passes the horizontal line test, and the reflection of a y equals x also works. So we're consistent from what we just talked about. Are you with me on that? Yeah, I'm losing you here. What's going on? Is it just, you just did this in last semester? Yeah, okay. So is that okay? See what happened? So what we call here, sometimes you can take a function that's not one-to-one, and you can restrict its domain to make it one-to-one in order to find the inverse. Now, there's one condition before we start doing that, before we start, limiting the domains of functions. It still has to span the entire range. I cannot just take a little chunk, say, hey, here's one-to-one part. It still has to cover the range of the original function. Otherwise, this whole exercise is useless. Because again, we're going to use inverses to solve equations. When you solve equations, you actually pick a number from the range, and you say, well, where did it come from? It came from there. So that's the solving equation, right? So it better work for every numbers in the range. With me? Okay. So if I give you this function, for example, f of x equals -2 absolute value of x plus 1 plus 1. Here's the function. Can I Can you sketch a graph of this function, first of all, based on what we discussed last week? So how would we go about that? So yeah, so it's the v. Where's the v going to go? So up 1 to the left, v, but what kind of v? What? Yeah, horizontal stretch, and the negative sign will also flip it. So it's kind of a skinny v like that, right? The 2 will make it skinny. But the point is, the only thing that really matters is this point right here, okay? So if I were to ask you, restrict the domain of this function so it's 1 to 1 and still covers the entire range, what is the very natural thing to do? Which part of this graph would you take so it remains 1 to 1 and covers the entire range? Yeah, so I mean, you can take either one of these, but you know, it feels good to take that chunk, right? If I consider this chunk, it is 1 to 1, right? It still covers the entire range. So the limiting the domain here would be if I just consider the domain from -1 to infinity, right? Because this is the x value here, -1. I will get a 1 to 1 function. Actually, it will just be, then you no longer need the absolute value, right? Because it guarantees to stay positive. So then the function will just be -2 times x plus 1 plus 1, and then you can just do your thing, okay? So we can do that. We can restrict domains to make our functions 1 to 1. Now, in this class, and I'm jumping a little bit ahead, we will see a graph like this. I'm jumping a little ahead. We will see a graph like this. It will just keep going, a little wavy thing. Okay, so it goes on forever and ever, just does the wavy thing. Some of you have seen graphs like that, whatever. Is this a 1 to 1 function? It's very far from it. It fails the horizontal line test in many places, right? Remember that. So you're going to have problems with doing inverses of these functions, right? Because again, we're going to have to solve equations that involve these functions, and the only way to do that is by using the inverses. Now, I'll give you some important points here. Like this point is pi, your favorite pi. That point is 2 pi. This point is pi over 2. This point is -pi over 2. This is -pi. So what we did, and that's what we agreed on in math, is, because there are so many options that you can do. You can take any one of those chunks that will span the range. Actually, the range of this function is from -1 to 1. It's always limited by those two numbers. So what we agreed to do is to take this part of the graph from this point all the way to this point. Is that chunk 1 to 1? Yeah? Still covers the range? Yeah? So the restrictions on the domain of this specific function, we did -pi over 2 to pi over 2. Right? So this was the domain. The range is from -1 to 1. That's ugly. Let me go right back. Okay? We can actually sketch that inverse. All I have to do is to flip them around x equals y or whatever. Is that okay? Again, we'll revisit this again later this semester when we actually know what the graph represents. There'll be another function that we'll look at. We're going to have this guy right here, which is very similar to what I just drew, only kind of shifted. And the important points will be things like pi over 2, pi, 3 pi over 2, 2 pi, -pi over 2, things like that. Okay. So what we did with this graph, again, very far from being one-to-one, right? So we did this part. We took this part of the graph. That part is one-to-one, right? Still covers the entire range. The range stays the same from -1 to 1. So the domain here was from 0 to pi, and the range was from -1 to 1. So we had to do that first in order to even start looking for the inverses of these functions. But those inverses now exist. So what is the domain of the inverse of that first function? That first function that I drew, after you restrict the domain, what is the domain of that inverse now? Yeah, so it's -1 to 1. That part stays consistent. The range becomes the domain. Domain becomes the range of the inverse. So the range of the inverse will be this. They interchange. Same happens here. The domain will be from -1 to 1, and the range will be from 0 to pi. Now, whatever this inverse is called, we don't know yet because we don't even know what this original function is called. And some of you do know that, but it's not official knowledge yet. Is that okay? All right. Is that good? Does that make sense? Is everybody on my math lab? Did it work for you? No? Okay. So you're able to access homework?
Yeah, I got onto it through, I already set up the trial version because apparently mine is invalid. It's not even like expired. It's like invalid.
Somebody used it, basically. I think that's what it
Well,
means.
yeah, I don't know. I'm just sending it back to Amazon, getting my money back and buying it off the thing. But the trial version lasts for 14 days. And the guy said it, you need to just call the company and like
Uh-huh.
tell you.
Is it 14 days from the beginning of the class or 14 days from your signing up?
14 days before you sign up, so just
Okay.
I lost.
Very good. I'm going to stop now because you guys are falling asleep and it's bugging me.